Hi students, in this video we're going to cover the last section of this unit, the fundamental theorem of algebra. So the fundamental theorem of algebra is based around complex numbers. So recall that a complex number is of the form a plus bi, and a and b are just any real number. So a or b could be zero. If a is zero, we have a pure imaginary number, and if b is zero, we have a pure we have a pure real number. And so all real numbers are complex numbers because the number 4 is, for instance, equal to 4 plus 0 times I. And so all real numbers are complex numbers. That's very important for this theorem. So the fundamental theorem of the algebra is that if a polynomial function has complex coefficients, which again, real numbers count, and the polynomial has a degree that is at least 1, the polynomial has at least one complex root. Now again, that's obvious because if we take an equation like 3x plus 1 equals, we'll just say 7, then this is a polynomial function. You know what? Make it a polynomial function. So if we have f of x equals 3x plus 1, then if we set this equal to 0, then you get 3x equals negative 1, x equals negative 1/3. And so remember, negative 1/3 is the same as negative 1/3 plus 0i. So that's our complex root. And so now if we extend this up to a polynomial, for instance, I could have a polynomial like g of x equals, we know quadratic could be like x minus 1 times x plus 2, and we get another solution. So we get at least one complex root. Technically, all of the roots are complex roots. The complex factorization theorem is if a polynomial has complex coefficients, again, real numbers count, and the degree of the polynomial is n, then if we include the multiplicity of a particular root, then the function has n complex roots. So that means that this 5th degree polynomial that we wrote, that we have below here, has 5 complex roots. And again, real numbers count as complex roots. So and we can express the polynomial as a factor of those roots. So if we see the function x to the 5th minus x to the 4th plus 7x cubed minus 7x squared plus 12x minus 12, we can completely factor that function down to x minus 1 times x minus I square root 3 times x plus I square root 3 times x minus 2i times x plus 2i. And so remember, complex roots occur in pairs. Square root, like irrational or solutions that have square roots, occur in pairs. So if you have one that's positive, you will always have the other that is negative. And that's the complex factorization theorem. Now, to do this stuff, we're going to have to use all of the methods of factoring that we know. Sometimes we'll have to do synthetic division. Sometimes we'll have to factor by grouping. Sometimes we'll have to recognize that things are in quadratic form. And all of those things are used to completely factor a polynomial. So our first example is we have to find all the solutions to the polynomial function and express the polynomial as a product of its linear factors. So we have this x to the 4th plus x cubed plus 7x squared plus 9x minus 18. So we don't know any of the roots. So what we'll have to do is use the rational root theorem, which says that if the function has rational roots, then we can take this value as p and the coefficient of the x to the 4th as our q and make a possible factor list of the p value, the factors of p divided by the factors of q. Now, fortunately, p divided by q is only going to be all of the factors of 18 divided by positive and negative 1. So we get 1, 2, 3, 6, 9, and 18. Now, so that's going to be just plus and minus for all of those. Now, again, this is a guessing check at this point. My recommendation is always start with the smaller numbers, plus or minus 1, plus or minus 2, and work your way up. I'm going to say we start with positive 1. And so remember, for this, we do synthetic division. So we're going to try synthetic division with x equals 1. Now, if x equals 1 works, it means that x minus 1 is a factor. So that's going to be important. So we have x equals 1, and then we write our value. So we have 1, 1, 7, 9, and negative 18. So remember, if we do synthetic division with a 4th degree polynomial, we get a 3rd degree polynomial as our result. So remember, for synthetic division, we bring down the 1. 1 times 1 is 1. 1 plus 1 is 2. 1 times 2 is 2. 7 plus 2 is 9. 1 times 9 is 9. 9 plus 9 is 18. And 1 times 18 is positive 18. So at the end, we do get a remainder of 0. So right now, we know one of our factors is x minus 1, and we know x equals 1 is a root or solution. So now the cubic equation that we get from this is f of x, we'll say f1 of x is, so that's x cubed, that's x squared, that's x, and this is our constant. So we're going to have 1x cubed plus 1x squared, plus 2x squared, plus 2x squared plus 9x plus 18. So from here, if the function didn't factor, we could use the same P over Q list again to try to find our solutions. Now, it turns out that we can factor by grouping, because x squared divides into those two terms and 9 divides into those two terms. So when we factor this, we get x squared times x plus 2 plus 9 times x plus 2, and that is x squared plus 9 times x plus 2. And now when we factor this, we see that x plus 2 is another linear factor. And so now we have to solve the x squared plus 9 to get our other two solutions. So if x squared plus 9 equals 0, that's the same as x squared equals negative 9, which means that x equals positive and negative square root of negative 9, which is plus or minus 3i. So our other two linear factors are x plus 3i, that gets us the root of negative 3i, and x minus 3i, which gets us the root of positive 3i. So when we say express this as linear factors, we mean that x is to the first power, and then we subtract our solutions. So our four solutions are x equals 1, x equals negative 2, x equals negative 3i, and x equals positive 3i. And again, you express your factors as, so if x equals 1 is a solution, x minus 1 is a factor. If x equals negative 2 is a root, x minus negative 2 is the factor. If x minus 3i is the solution, x minus negative 3i is a root, and then x minus 3i is the other root. And so again, this is how we express that as the product of those linear factors. Number 2, given that x equals 1 is a solution to that polynomial, we need to completely factor the polynomial and find all solutions. So again, knowing that x equals 1 is a solution is important because it allows us to do synthetic division. So we're going to do x equals 1, and we're going to put in 1, negative 1, 7, -7, 12, and -12. And we'll bring down the 1. 1 times 1 is 1. -1 plus 1 is 0. 1 times 0 is 0. 7 plus 0 is 7. 1 times 7 is 7. -7 plus 7 is 0. 1 times 0 is 0. 12 plus 0 is 12. 1 times 12 is 12. -12 plus 12 is 0. So we started with the 5th degree, so we're going to have x to the 4th, 0x cubed, 7x squared, 0x, and a constant of 12. So right now we can write f of x equals, all right, so we're going to express this as a factor. So since x equals 1 is a solution, x minus 1 is the factor. So now we get our reduced polynomial is f of x equals x to the 4th plus 7x squared plus 12. So now this is quadratic in form because the degree is twice as much as that middle term, and the last term is a constant. So we can factor this just like we would factor f of x equals x squared plus 7x plus 12. We just need factors of 12 that add to be 7. So we're going to have x squared for both our binomials. So we're going to have x squared, and the factors of 12 that add to be 7 are plus 4 and plus 3. And so now we have two simple quadratic functions to solve. So we have x squared equals -4, which means that x equals plus and minus 2i. And we have x squared equals -3, which means that x equals plus and minus I square root 3. So in the case, so let's write all our solutions. We'll write these over here. So we get x equals, we already know x equals 1 is a solution. We know x equals 2i is a solution. We know x equals -2i is a solution. We know x equals I square root 3 is a solution. And we know, x equals -I square root 3 is the other solution. So if we express this as a product of linear factors, let's get some room. We'll have f of x equals x minus 1 times x minus 2i times x plus 2i times x minus I square root 3 times x plus I square root 3. And that is how we express that function as a product of linear factors. We only have one real number solution and 4 complex solutions. Again, the complex solutions occur in pairs, and the square root solutions also occur in pairs, one positive, one negative. Example 3 is, we know that x equals -1 has a multiplicity of 2 for the function g of x equals that thing. And we need to find the remaining roots for the polynomial and completely factor the polynomial. So x equals -1 having a multiplicity of 2 means that we can do synthetic division with x equals -1 twice. So let's do that. So we're going to have -1, and we're going to put -3, -8x cubed, -12x squared, -12x, and -5. And we'll bring down the -3. -1 times -3 is 3. -8 plus 3 is -5. -1 times -5 is 5. 5. -12 plus 5 is -7. -1 times -7 is 7. Why did I write 5? -12 plus 7 is -5. And -1 times -5 is +5. negative 5 plus 5 is 0. So now we get a 3x cubed, negative 3x cubed, negative 5x squared, negative 7x, and a constant. But since the negative 1 has a multiplicity of 2, it means that we can take the values that we have in the bottom row and do synthetic division again to get a quadratic function that we can either factor or do the quadratic formula. So we're going to put in now negative 3, negative 5, negative 7, and negative 5. We're going to bring down the negative 3. So negative 1 times negative 3 is 3. Negative 5 plus 3 is negative 2. Negative 1 times negative 2 is 2. Negative 7 plus 2 is negative 5. And negative 1 times negative 5 is 5. Negative 5 plus 5 is 0. So again, the multiplicity of 2 helps us do synthetic division twice. And so now we have this reduced polynomial of f of x is negative 3x squared minus 2x minus 5. And let's see, that either factors or you can use a quadratic formula. I generally say in the interest of time, just do the quadratic formula. So we'll get x equals the opposite. So we have a, b, and c. So the opposite of negative 2 is 2 plus or minus the square root of b squared minus 4ac. So negative 2 squared minus 4 times negative 3 times negative 5, all divided by 2 times negative 3. And if we simplify that, we get 2 plus or minus the square root of, so that's going to be 4 negative 12. So positive 12 times negative 5 is negative 60. So 4 minus 60, that's going to be the square root of negative 56, all divided by negative 6, is it? So if we simplify this, I would actually say you could leave it like this for me. But up here, the square root of 56 in terms of perfect squares is 4 times 14. So this is 2 square root 14. So when we simplify this, it's 2 plus or minus I. I'll take that back. Need my eraser. Excuse me. We get 2 plus or minus 2i square root 14 divided by negative 6. And that's going to give us, everything is divisible by 2. So we get 1 plus or minus I square root 14 divided by negative 3. So our solutions are, let me get some room here. So we know negative 1 is one of our solutions. So let me erase this. Go back to our pencil. So let's see. One solution is x equals negative 1. The other solution is x equals negative 1 because of the multiplicity of 2. And then our other solutions are x equals negative 1/3 minus I square root 14 over 3 and negative 1/3 plus I square root 14 divided by 3. So if we have to express this as a product of factors, we'll have g of x equals x plus 1 squared because of the multiplicity of 2, and then x minus negative 1/3 minus I square root 14 over 3, and the other factor is x minus negative 1/3 plus I square root 14 all divided by 3. So now that seems like a lot, but all we did was synthetic division twice, use the quadratic formula, got our roots, use those roots to make a product of linear factors. All right, so that concludes this video on the fundamental theorem of algebra and the complex factorization theorem. So there are too many problems to work each type. Just know that between synthetic division, factoring by grouping, quadratic form, quadratic formula, and factoring out the greatest common factor, there are many ways to factor factorable polynomials. And then for the ones that can't be factored, you won't ever see those on the test. All right, thanks for watching.